For 9.5 years, the spacecraft transmitted almost nothing. Not because something went wrong, because there was nothing to say. Engineers had put New Horizons into hibernation mode for the bulk of its journey. Most systems powered down, the probe essentially asleep in the dark, crossing the solar system at speeds no human-built object had ever sustained for so long. Once a year, they woke it up, ran diagnostics, confirmed it was still there, still working, still moving, then put it back to sleep. 4.67 billion miles of silence. And then, in the early hours of July 14th, 2015, everything that had been wrong about Pluto started becoming visible. Not all at once. The team at the Johns Hopkins Applied Physics Laboratory had to wait. New Horizons was performing its observations autonomously, executing a sequence of hundreds of pre-programmed commands, turning its cameras, activating spectrometers, pointing its antenna, all while moving too fast to be controlled in real time. The distance between Earth and Pluto meant that a signal took 4 hours and 25 minutes to travel one way. There was no back and forth, no course corrections, no human hand on the wheel. The spacecraft had to do it alone, and it did. At 7:48 p.m. Eastern Time that evening, New Horizons made contact, sent a status signal back to Earth, and the scientists confirmed it had survived. It had worked. The data was waiting. What came back over the following 16 months, because that's how long it took to download everything? 1.4 kilobits per second across 3 billion miles. Trickling in for a year and a half was a portrait of a world that shouldn't have been what it was. Not just surprising, not just more complex than expected. Wrong. Systematically, specifically, embarrassingly wrong in ways that rewrote what we thought we knew about how planets die, how the solar system works, and whether the word dead means anything at all when applied to a world this far from the sun. Tonight, we're going to go through what New Horizons actually found. Not the simplified version, not the highlight reel. The specific things, the specific numbers, the specific discoveries, the specific anomalies that made scientists say, "That's impossible," before realizing they had to revise their definitions of impossible. Before we go in, subscribe to Calm Theory for Sleep if you're new here. Like the video, and tell us in the comments where on this planet you're listening from tonight. We genuinely read every location, and knowing where this conversation is reaching matters to us. Now, let's go to Pluto. The history of a discovery is always partly the history of what everyone assumed before the discovery happened. And in Pluto's case, the assumptions were confident, detailed, and almost completely incorrect. By the time New Horizons launched in January 2006, planetary scientists had been studying Pluto for 76 years, since Clyde Tombaugh first spotted it in February 1930, while systematically photographing the sky at Lowell Observatory in Arizona. In those 76 years, with increasingly powerful telescopes, they had learned the basics. Pluto's size, roughly 2,377 kilometers in diameter, about 2/3 the diameter of Earth's moon. Its mass, roughly 0.2% of Earth's mass. Its composition, dominated by rock and ice. Its distance, averaging about 5.9 billion kilometers from the Sun, so far out that sunlight takes roughly 5.5 hours to reach it, arriving with less than 1,000th the intensity that reaches Earth. From these basics, a consensus had built about what Pluto must be like. Cold, obviously. Pluto's surface temperature was expected to average around -230 degrees Celsius, close to the theoretical lower limit for any solar-warmed surface anywhere in the solar system. At those temperatures, Nitrogen and carbon monoxide and methane, volatile compounds that would be gases on Earth, are solids, frozen into the surface, rock hard, geologically dead. This was the central assumption, and it was based on sound reasoning. Geological activity, volcanism, tectonics, resurfacing requires an internal heat source. In planets, that heat comes from three places: residual heat from formation, heat from the decay of radioactive elements, and tidal heating from gravitational interactions with moons or other bodies. Pluto was tiny. It had been slowly losing any formation heat for 4.5 billion years, and a body that small loses heat relatively quickly. Its radioactive element content was modest, and its gravitational relationship with its largest moon, Charon, had long since tidally locked the two bodies. They always show the same face to each other, like two dancers facing each other without turning away, which means the tidal flexing that heats moons like Io or Europa around Jupiter doesn't operate at Pluto. By every calculation, Pluto should have been geologically inert for billions of years, heavily cratered. Geologically dead worlds accumulate craters the way a car accumulates dust, continuously, passively, with no mechanism to erase the marks of impacts. Mercury is heavily cratered. The Moon is heavily cratered. Mars, mostly dead geologically, is heavily cratered across much of its ancient surface. Pluto, old and cold and geologically inert, should be among the most cratered objects in the solar system. Simple, small, boring. The team at the Southwest Research Institute, who built and operated New Horizons, had to justify the mission's $720 million budget to skeptics who questioned whether Pluto was worth that investment. Even some planetary scientists were uncertain. There were legitimate questions about whether the flyby would reveal anything that couldn't be inferred from Earth-based observations. Those questions were answered within hours of the first images arriving. Not gradually, not in the way science usually works, where conclusions build slowly from accumulating evidence. Immediately, visibly, unmistakably, from the very first high-resolution image that resolved Pluto as a world rather than a dot. The surface was not heavily cratered. It was not geologically inert. And in one specific region, a region shaped unmistakably, uncannily, like a heart. It was not just active but continuously, currently, actively renewing itself, erasing its own history, generating new surface in real time. Pluto was alive, in the most technical geological sense of that word, alive. The first image that resolved Pluto clearly enough to show surface features, released to the public before the closest approach, when New Horizons was still 2 days out, showed a bright, roughly heart-shaped region on the surface. The team named it informally after Clyde Tombaugh, the man who found Pluto, Tombaugh Regio. It became, overnight, one of the most recognized images from any space mission since the Apollo photographs of Earth from the Moon. But the visual appeal of the heart shape, the fact that it looked like a symbol of affection, that it made Pluto feel suddenly warm and endearing rather than cold and distant, obscured what was actually scientifically significant about it, which is this: the heart is a geological catastrophe and a geological wonder simultaneously, and the two facts are related. The heart is a basin. Specifically, it's an ancient impact basin, a crater so large that calling it a crater understates it. At roughly 1,000 kilometers across and 3 to 4 kilometers deep, Tombaugh Regio is not a mark on the surface. It is a reshaping of the surface. Something enormous struck Pluto billions of years ago and tore out a chunk of crust across an area slightly larger than Texas. Over time, something happened to that basin that had no precedent in any previous planetary study. It filled with nitrogen ice. Not a thin coating, not a veneer. A deep, flowing sea of nitrogen ice that now sits in the basin at depths of several kilometers. Contained on its northern and western sides by the elevated walls of the original impact structure, and sloping more gently toward the south and east, where the basin margins are lower. This nitrogen ice is not static, it is moving. Slowly, the rates are measured in centimeters per year, but actively, currently flowing. And it's not just flowing in one direction, it is convecting. The mechanism is the same mechanism that drives a pot of boiling water, applied to a solid. Within the deep nitrogen ice of Tombaugh Regio, the bottom of the ice layer is slightly warmer than the top, warmed by Pluto's interior heat, which we'll discuss in detail, while the top is cooled by exposure to the near absolute zero of Pluto's surface temperature. This temperature difference drives a slow circulation. Warm ice at the bottom becomes slightly buoyant, rises. Cool ice at the top becomes slightly denser, sinks. The ice turns over in enormous slow loops. This convective overturn is what produces the polygon shapes visible in the basin. Giant cells, 20 to 40 kilometers across, each one the top of a convection cell, defined by the troughs where descending cool ice meets ascending warm ice along the cell walls. Pluto's surface is divided into these shapes the way the top of a pot of thick oatmeal shows cells when it simmers. The consequence is that the surface of Tombaugh Regio is continuously refreshed. The nitrogen ice at the surface is constantly being removed by sublimation, the direct conversion from solid to gas in Pluto's thin atmosphere, and constantly replaced from below as the convection cycle brings fresh material up. Meteorites that land in Tombaugh Regio are covered and erased within geologically brief timescales. The surface is young because it is continuously being made new. How young? The team estimated, based on crater counts in the region, essentially zero. Accounting for the expected flux of Kuiper Belt impactors, that the surface of Tombaugh Regio's youngest regions is no more than 10 million years old. In a solar system that is 4.5 billion years old, 10 million years is essentially yesterday. The surface of Pluto's heart is younger, in geological terms, than some mountain ranges on Earth. This was not predicted, not even in the most optimistic models. A geologically dead world 5.9 billion kilometers from the Sun, smaller than Earth's moon, having actively renewed its own surface within the last 10 million years. This violated essentially every assumption underlying the pre-Flyby consensus. And the heart was only the beginning. Before we continue through the discoveries, it's worth understanding how the New Horizons science team actually received its data, because the structure of the download shaped the entire narrative of discovery in ways that are rarely explained. New Horizons had a radio transmitter operating at 15 watts. 15 watts. The power of a dim light bulb. Broadcasting across more than 4.6 billion miles of space to antennas 70 meters in diameter on Earth. The Deep Space Network dishes in Goldstone, California, Madrid, Spain, and Canberra, Australia. The signal that arrived after that journey was unimaginably faint, requiring multiple receiving dishes and hours of integration to extract reliable data. The maximum data rate achievable given these constraints, approximately 1 to 2 kilobits per second. The total amount of data stored on New Horizons' solid-state memory after the flyby, approximately 50 gigabits. At 1 to 2 kilobits per second, transmitting 50 gigabits takes roughly 16 months. The team knew this before launch. They planned for it. They had prioritized the data storage on New Horizons so that the most important observations were transmitted first. The close approach images of Pluto's surface, the atmospheric measurements, the Charon flyby data. Scientifically lower priority data came later, sometimes arriving many months after the closest approach. The practical consequence was extraordinary. The science team spent a year and a half in a state of sustained discovery. Every week, new data packets arrived. Every week, images or spectra or particle measurements or plasma readings appeared on the team's screens that nobody had seen before. Discoveries that would have been front-page news if they'd all arrived at once were instead distributed across 16 months, each one building on the last. The team described this as being like Christmas every week, but a version of Christmas where you ordered an enormous number of packages, carefully prioritized by importance, and they arrived one by one over a year and a half. The most eagerly anticipated packages came first, but some of the most scientifically surprising ones came later, when the raw excitement of the close approach images had settled and scientists could look more carefully at what the data was actually saying. What it was saying was a story of progressive surprise, a world that had more anomalies, more unexplained features, more violations of expectation, the more carefully it was examined. One of the first close approach images to arrive showed a region along the edge of Tombaugh Regio, in an area that had been named informally after the Hillary and Tenzing Norgay, the first climbers of Everest. What the image showed stopped the geology team cold. Mountains. Not gentle undulations. Mountains. Jagged, angular, reaching elevations of 3,000 to 4,000 meters above the surrounding plains, comparable in height to the Alps or the Rocky Mountains, with slopes steep enough that the team initially questioned whether they were interpreting the image correctly. These mountains were completely unexpected, not because mountains are unusual. Earth has them, Mars has enormous volcanic ones, Io has mountain ranges, but because mountains of this kind require a specific ingredient, structural mountains, the kind built by tectonic forces or the remnants of ancient geological upheaval, require that the material they're made of be rigid enough to support its own weight over billions of years. Rock can do this. Water ice, under Earth conditions, cannot. It flows. Ice glaciers creep downhill under their own weight over decades. A mountain range of water ice, at Earth temperatures, would slump and flow away before it reached alpine heights. At Pluto temperatures, this changes. At -230 degrees Celsius, water ice doesn't flow. It is rigid, in the way that silicate rock is rigid. Its crystal structure is locked in place by the extreme cold. The viscosity of water ice at Pluto's surface temperature is comparable to granite. It behaves, for geological purposes, as rock. Pluto's mountains are made of water ice. Water ice in the role of bedrock, the structural foundation of the planet's surface geology, not a thin coating of ice over rock beneath, as on Earth's glaciers. Water ice all the way down, functioning as the geological substrate of the entire world. This was the first demonstration of a principle that would be confirmed again and again as the data arrived. At Pluto, the materials that we think of as delicate or temporary on Earth, water, nitrogen, methane, take on the roles that hard, permanent materials play in familiar geology. Water is rock. Nitrogen is the material that flows and deposits, the way liquid water behaves on Earth. Methane is the volatile that drives precipitation and erosion. The whole geological system is transposed. Understanding Pluto requires rethinking what each substance does when temperature is reduced by 200 degrees below anything in human experience. This transposition of material roles is clearest in the nitrogen cycle, which turns out to be one of the most scientifically important discoveries of the entire mission, and one that almost no popular treatment of the New Horizons data explores in adequate depth. On Earth, the water cycle is the engine of surface geology. Water evaporates from the ocean, forms clouds, falls as rain and snow, erodes rock surfaces, carries sediment, deposits it elsewhere, fills rivers and lakes, and eventually flows back to the ocean. The entire shape of Earth's continents, every valley, every delta, every canyon, is partly the product of this cycle. Pluto has an analogous cycle, running on nitrogen instead of water, with methane playing the role of precipitation in certain regions. Nitrogen ice covers significant portions of Pluto's surface, concentrated most densely in Tombaugh Regio, but present elsewhere as well. This nitrogen is in a delicate equilibrium. On the sunlit, warmer side of Pluto, nitrogen sublimates, converts directly from solid to gas, and enters the atmosphere. It circulates in Pluto's thin atmospheric winds, gets transported to other regions. On the colder, shadowed side of Pluto, atmospheric nitrogen condenses back into solid ice on the surface. This seasonal cycle of sublimation and deposition means that nitrogen ice is continuously moving around Pluto's surface, flowing from regions of net sublimation toward regions of net deposition, accumulating in basins and low elevation regions where it can pool and build up depth. The current accumulation of nitrogen ice in Tombaugh Regio, kilometers deep, thousands of kilometers across, is the product of this cycle over geological time. The basin that formed from an ancient impact became the lowest point, and the nitrogen, following the same thermodynamic logic that drives water into ocean basins, has been filling it ever since. There is even glacial flow. On the southwestern margin of Tombaugh Regio, New Horizons detected what appears to be nitrogen ice glaciers flowing out of the heart and into the adjacent highlands, carving channels, forming lobes and flow fronts, with the characteristic shapes of glacial tongues. Nitrogen glaciers on Pluto, flowing the way ice glaciers flow on Earth, driven by the same gravitational imperative of ice flowing downhill under its own weight. The difference is that these glaciers aren't flowing slowly over centuries as Earth's glaciers do. They're flowing over geological epochs, because at Pluto's temperatures, even the flow rate of nitrogen ice is orders of magnitude slower than water ice on Earth. What looks in New Horizons' images like frozen flow features has been developing over millions of years. And there's a second volatile cycle overlaid on the nitrogen cycle. Methane on Pluto behaves more like water does in Earth's alpine zones. It precipitates out at high altitudes, forming a frost, then either stays frozen or sublimates as temperature permits. The specific distribution of methane frost on Pluto was one of the surprises of the flyby. It's not uniformly distributed, but concentrated in specific regions determined by the combination of topography and exposure to solar radiation, which leads to one of the strangest features New Horizons discovered. In the eastern part of Pluto, in a region that had been named Tartarus, after the deep abyss in Greek mythology, New Horizons cameras found something that made the geology team stare at the images for a long time before anyone spoke. Blades. Enormous blades of methane ice, rising directly from the surface, packed tightly together, pointing upward at angles from near vertical to slightly leaning. Hundreds of them, some reaching 300 to 500 meters in height, comparable to skyscrapers, extending across an area hundreds of kilometers wide, covering the terrain in a dense forest of sharp-ridged icy blades that made travel across the surface essentially impossible to imagine. Nothing like this had ever been seen anywhere in the solar system. The initial reaction was puzzlement. Methane ice shouldn't form this way. It shouldn't grow in blades. The physics of how crystalline ices form under normal conditions doesn't produce vertical blade structures at this scale. Something specific to Pluto's environment must be responsible. The answer took several months of analysis to work out, and it turned out to depend on a specific interaction between altitude, sunlight, and the sublimation of methane. The key observation: Tartarus dorsa exists almost exclusively above a certain elevation. Below, roughly 2,000 to 3,000 meters above the surrounding plains, the bladed terrain disappears. Below that elevation, the surface is relatively smooth, and bladed terrain is absent. Above it, the blades are everywhere. This altitude correlation is the clue. At high altitudes on Pluto, the combination of lower atmospheric pressure and exposure to direct sublimation by sunlight creates specific conditions for how methane ice is removed from the surface. Sublimation under these conditions doesn't remove ice uniformly. It preferentially attacks the lower, more exposed parts of any ice mass, eating away the bases of ridges and hills while leaving the higher points more protected. Over time, this sculpts the original ice into increasingly blade-like forms, the same way wind can sculpt sand into sharp ridges. The process is analogous to something observed in Earth's high-altitude deserts. On tropical mountainsides at high elevation, particularly in the Andes, there are formations called penitentes, spikes of ice or snow that form when ablation, the removal of ice by sublimation or melting, preferentially attacks low points between spikes, leaving the high points as sharp blades. Earth penitentes are typically centimeters to a meter tall. Pluto's bladed terrain is the same process at a scale of hundreds of meters, operating over millions of years instead of seasons. The discovery that Tartarus dorsa is essentially giant penitente rain simultaneously explained its existence and raised a deeper question. What happened to put so much methane ice at those high elevations in the first place? The current best answer involves Pluto's ancient history, periods when the planet's atmospheric composition was different, when methane was more abundant and deposited differently than it does now. The blades are a fossil of an earlier atmospheric regime, preserved in methane ice, sculpted into their current dramatic form by sublimation over millions of years. Tartarus dorsa is, in this sense, a geological record, a record carved in methane ice of conditions on Pluto that no longer exist. A message from a different era in Pluto's history, legible in the shapes of spires tall enough to scratch the sky. New Horizons' closest approach gave it a unique observational opportunity that no Earth-based telescope could replicate. As the spacecraft passed behind Pluto relative to the Sun, sunlight passing through Pluto's atmosphere and reaching New Horizons instruments was filtered by the atmospheric composition in ways that revealed its chemistry in detail. What the data showed was an atmosphere far more complex than anyone had predicted. Pluto's atmosphere is thin, roughly 100,000 times thinner than Earth's at sea level, with a surface pressure of about 10 microbars compared to Earth's 1 bar. But thin does not mean simple. The atmosphere has layers, distinct chemically differentiated layers that process sunlight differently, react with incoming solar radiation differently, and contribute to Pluto's surface chemistry differently. New Horizons detected 12 distinct haze layers in Pluto's atmosphere, stacked one above the other, like geological strata, each at a specific altitude range, each with a specific composition and a specific set of chemical reactions taking place within it. The haze itself was unexpected. Astronomers had known Pluto had an atmosphere and had known it was primarily nitrogen, with trace amounts of methane and carbon monoxide. But they had assumed this thin, cold atmosphere would be relatively clear. That, with so little gas and so little solar energy arriving, there wouldn't be enough photochemistry to produce the complex organic compounds that generate visible haze. They were wrong about the amount of chemical activity. Ultraviolet photons from the Sun, arriving at Pluto with less than 1,000th of the intensity they reach Earth, are nonetheless sufficient to drive photochemical reactions in Pluto's upper atmosphere. Methane molecules are broken apart by ultraviolet radiation. The resulting molecular fragments, methyl radicals, hydrogen atoms, other reactive species, combine in complex reaction chains that produce heavier organic molecules. These heavier molecules, including tholins, complex reddish organic compounds, are too heavy to stay in the gas phase at Pluto's atmospheric temperatures. They form tiny particles, aerosols, haze. The haze particles are small enough that the atmosphere is not opaque. You could still see the surface from orbit, and the sun's light still reaches the surface. But the haze scatters blue light in ways that make the atmosphere appear blue when viewed against the darkness of space, in exactly the way Earth's atmosphere appears blue when viewed from the side. The same Rayleigh scattering of short-wavelength light that gives Earth its blue sky. The famous image of Pluto's blue atmospheric haze, released by NASA and shared globally within days of the flyby, shows Pluto's atmosphere backlit by the sun, a crescent world in deep shadow, its edges glowing with the blue of scattered sunlight in the haze. The image is beautiful. It is also chemically revealing. The 12 distinct layers in the haze correspond to 12 distinct zones of chemical processing, each with its own photochemical reactions, each producing its own mixture of organic compounds. These compounds eventually settle. They drift downward through the atmosphere, through each layer, and when they reach the surface, they deposit. The reddish organic compounds, the tholins, accumulate on Pluto's surface in the regions where the atmosphere cycles them down. This is the origin of the dark, reddish terrain in Kuiper Regio and other dark patches on Pluto's surface, not ancient, unchanged rock. A continuous accumulation of organic material produced in the atmosphere by photochemistry and settled to the surface like a slowly falling red snow. Pluto is coating itself in organics, continuously, right now. Pluto's largest moon, Charon, received a close look from New Horizons during the same flyby. The spacecraft's trajectory was calculated to pass closest to Pluto, but within range for detailed imaging of Charon as well. What New Horizons found there connected back to Pluto in a way that nobody had anticipated. Charon's North Pole is dark. Not uniformly dark, not the same as the surrounding terrain. Specifically, anomalously dark, with a reddish-brown coloration distinct from everything else on the Moon's surface. This dark polar cap has been visible in Hubble Space Telescope observations for years, but the mechanism that produced it was unknown. New Horizons' observations provided the answer, and the answer implicates Pluto directly. Pluto's atmospheric gases, specifically nitrogen and methane, are continuously escaping from Pluto into space. The escape rate is not catastrophic, not a rapid depletion, but ongoing, driven by the slight excess of molecular velocities at the top of the atmosphere that exceeds Pluto's escape velocity. A portion of these escaping gases is captured by Charon's gravity and temporarily settles onto Charon's surface. Particularly at the poles, during Charon's long winter seasons, when the poles are in extended darkness and therefore cold enough to trap and hold atmospheric molecules. During winter on Charon's North Pole, which lasts for decades given Pluto's 248-year orbital period, escape nitrogen and methane from Pluto freeze onto the polar surface. When the long polar summer arrives and sunlight hits the pole again, ultraviolet radiation drives photochemistry in these frozen deposits. Methane, in particular, is converted by UV radiation into tholins, those same reddish organic compounds that Pluto's atmosphere produces and deposits on its own surface. The difference at Charon is that during the summer, most of the volatile gases, nitrogen and methane, sublimate and return to space. But the tholins, the heavier, more complex organic compounds, don't. They're too stable, Too difficult to remove by sublimation at these temperatures, they remain on the pole. Accumulating, over millions of years of seasonal cycles, the Tholen deposit builds up. Layer by layer, each polar winter adding another increment. Each polar summer fixing it more permanently into the surface. Charon's red pole is Pluto's exhalation made visible. It is the record of billions of years of Pluto's atmospheric escape, accumulated on its companion's surface. Pluto has been painting Charon red for as long as both have existed. This discovery has a specific scientific importance that goes beyond its visual drama. It means that the organic material produced in Pluto's atmosphere, the photochemical output of billions of years of UV-driven methane chemistry, is not just depositing on Pluto. It's being distributed into the surrounding space. Charon is covered in it. The smaller moons of Pluto may carry it too, though they're too small for New Horizons to have imaged in the same detail. And some fraction of this material must be escaping the Pluto-Charon system entirely and entering the broader Kuiper Belt. Pluto is a chemical source, producing complex organic compounds and distributing them outward into the solar system. The implications for the broader chemistry of the outer solar system are still being worked out. But the principle is established. Pluto is not just an isolated object sitting quietly at the edge of the solar system. It is interacting with its environment, contributing to the chemistry of the space around it, leaving its chemical signature on the objects nearest to it. Most attention on the Pluto system focuses on Charon, and reasonably so, since Charon is enormous relative to Pluto, roughly half Pluto's diameter, containing about 1/8 of Pluto's mass. The Pluto-Charon system is unique in the solar system. They are the only known pair of objects where both members are large enough relative to each other that their common center of mass, the barycenter, lies in the space between them rather than inside the larger body. They orbit each other. They orbit a point in empty space. But there are 4 other moons in the Pluto system, all much smaller, discovered by Hubble Space Telescope observations between 2005 and 2012, Nix, Hydra, Kerberos and Styx. New Horizons provided the first close-up views of Nix and Hydra in particular, and what it found about their behavior was genuinely unexpected. They tumble, not in the way that most moons in the solar system rotate. Most moons rotate in a stable, predictable way, synchronized to their orbital period or following well-understood rotational dynamics. Nix and Hydra, and probably Kerberos and Styx, rotate chaotically. Their rotation rates change. Their rotation axes shift. They are in a state of permanent gravitational chaos, driven by the complex, constantly changing gravitational environment produced by the Pluto-Charon binary. The problem is this. Charon's gravitational influence on the small moons is so large and varies so dramatically as Pluto and Charon orbit their common center of mass that any simple rotational equilibrium is impossible to maintain. The small moons receive constant gravitational kicks that destabilize whatever rotation state they approach. Computer models of the system, which work perfectly well for simple planet-moon systems, fail when applied to the Pluto system's small moons. The predicted rotation behaviors don't match the observations. This isn't a failure of physics. It's a demonstration that the Pluto system is genuinely more dynamically complex than any analogous system we've studied. The gravitational environment produced by a near-equal mass binary pair creates dynamical conditions that have no good parallels elsewhere in the solar system, and the small moons are embedded in this environment and subject to its effects. The practical consequence: if you stood on Nix, the sky above you would not behave predictably. Pluto and Charon, viewed from Nix's surface, would appear to move in complicated, sometimes erratic ways. As Nix's own tumbling changed the direction you were facing, relative to the binary pair. The sun would rise and set at irregular intervals, from apparently random directions. Time would be measured differently, because the familiar astronomical cycles that we use to define time on Earth, the regular rotation of the planet, the regular orbit of the Moon, would not apply. We've mentioned Pluto's internal heat repeatedly. It's necessary for the convection in Tombaugh Regio. It's implicated in the cryovolcanism that has been suggested by the landforms. But we haven't been specific about where this heat comes from. And the answer is worth sitting with, because it changes the picture of what Pluto is. The heat has two sources, and both are related to Pluto's composition, rather than to any ongoing dynamic process. The first source is radiogenic heat, the heat produced by the decay of radioactive elements. Pluto's interior is approximately 70% rock by volume, based on its bulk density and the known properties of rock and ice at Pluto pressures. This rock contains radioactive isotopes: uranium-235, uranium-238, thorium-232, and potassium-40. These isotopes decay at known rates, releasing energy as they do. The energy takes the form of heat, produced in the rock and slowly conducted outward. In larger rocky bodies, planets like Earth, the total radioactive heat production is enormous, contributing significantly to the internal heat that drives plate tectonics and volcanism. In a body as small as Pluto, the total production is much lower, but not zero. At 70% rock content, Pluto has enough radioactive material in its interior to produce meaningful heat over geological time. The second source, which may be significant in Pluto's specific case, is the heat preserved from the accretion process. When Pluto formed, approximately 4.5 billion years ago, it assembled from smaller bodies in the early solar system, a process that involved countless collisions. Each collision released kinetic energy, converting the incoming body's velocity into heat at the point of impact. This heat, accumulated over the relatively brief period of Pluto's formation, was partially trapped in the interior and has been slowly radiating outward ever since. The question is whether these two sources, radiogenic decay and residual formation heat, are sufficient to maintain a liquid water ocean beneath Pluto's ice shell for 4.5 billion years. The answer, according to the most detailed thermal models developed after the New Horizons flyby, is probably yes, but only with help from chemistry. The ocean that may exist beneath Pluto's ice shell, at depths of perhaps 100 to 180 kilometers, is not pure water. It contains dissolved ammonia. Possibly a lot of ammonia. Some models suggest concentrations of 20 to 30% by weight. Ammonia is an antifreeze. It lowers the freezing point of water dramatically. A mixture of water and 35% ammonia freezes at minus 97 degrees Celsius rather than the 0 degrees of pure water. Even at Pluto's frigid interior temperatures, an ammonia-rich water mixture can remain liquid. This is what the mission's chief scientist, William McKinnon, was describing when he called the hypothetical ocean a syrup, not water, not the water we think of when we imagine an ocean. A cold, viscous, ammonia-rich liquid with properties distinctly unlike anything in Earth's ocean chemistry. Whether this ocean exists is still not confirmed. It is inferred from the evidence, from the surface cracks that suggest expansion from freezing, from the shape of the impact basins that seem inconsistent with a fully frozen interior, from the heat flow implied by the active geology at the surface. But no spacecraft has yet drilled through Pluto's ice shell. No instrument has directly detected the ocean. What New Horizons established is that the conditions necessary for such an ocean, sufficient internal heat, sufficient chemistry, are plausibly present at Pluto. Before the flyby, an ocean at Pluto was considered essentially impossible. After, it became a legitimate scientific hypothesis that most planetary scientists take seriously. Tonight, we've covered the specific discoveries of the New Horizons mission, what scientists expected, why they were wrong, and what they found instead. The heart that's younger than Earth's mountain ranges. The water-ice mountains. The nitrogen cycle and its glaciers. The blade fields carved by sublimation. The 12-layer atmosphere glowing blue. The subsurface ocean that might be liquid. The cryovolcanoes that might still be erupting. The 4 moons tumbling chaotically in a gravitational field no model fully describes. The fresh ammonia that proves Pluto's interior is still reaching the surface today. And the overarching discovery that contains all the others. Pluto is not what we thought it was. Not a dead, cratered ball at the edge of the solar system. A world, active, complex, chemically rich, geologically young, in ways that force a revision of everything we thought we understood about how small, icy bodies behave at the far edge of a solar system. The specific wrongness of the pre-flyby consensus is not an embarrassment for planetary science. It is how science works at the frontier. You make your best predictions from available data. You build a spacecraft and send it across 4.67 billion miles. You wait 9.5 years, and when the data comes back, trickling home at 1 kilobit per second, one discovery at a time, over 16 months of sustained scientific surprise, you revise. The revision that Pluto required was not small. It was a rewrite of the foundational assumptions about the outer solar system. Assumptions that, as we look at the rest of the Kuiper Belt with new eyes, are going to keep being challenged. 6 months after New Horizons launched toward Pluto, Pluto stopped being a planet. Not because of anything New Horizons found. The spacecraft was still years from its destination. But because of a vote. A specific vote, on a specific day, by a specific group of people, that has been contested and debated and quietly resented by a significant portion of the scientific community ever since. The International Astronomical Union is the body that has official authority over the naming and classification of celestial objects. Every 4 years, it holds a General Assembly, a gathering of professional astronomers from around the world. In August 2006, the General Assembly was held in Prague. It was the year New Horizons was flying toward Pluto, the year the spacecraft was committed to its trajectory, and it was the year the IAU decided to formally define, for the first time in history, what a planet actually is. The definition they adopted has 3 criteria. An object must orbit the Sun. It must have sufficient mass for self-gravity to pull it into a roughly spherical shape. And this is the criterion that removed Pluto from the planetary category. It must have cleared its orbital neighborhood of other bodies. This 3rd criterion is the problematic one, and understanding exactly why reveals something important about how scientific classification actually works, and why the Pluto demotion was always about politics as much as physics. Pluto, in its orbit around the Sun, shares the Kuiper Belt with thousands of other objects. It has not gravitationally dominated its orbital neighborhood the way Jupiter has dominated its neighborhood, sweeping out debris, capturing moons, ejecting objects on crossing trajectories. By this criterion, Pluto fails. It is a dwarf planet, not a planet. But here is the specific number that the demotion's critics always cite. 424 astronomers voted on that final day in Prague, out of a total IAU membership of approximately 10,000 professional astronomers worldwide at the time. And even among those 424 who voted, the resolution passed by 424 to 333, with 91 abstentions. It was not unanimous. It was not even close to unanimous among those present. Less than 5% of the world's professional astronomers voted on the definition, that reclassified Pluto. And the definition they chose has a specific flaw that planetary scientists who study Pluto have pointed out repeatedly. The criterion of clearing the orbital neighborhood is not a binary yes-no property. It is a continuum. Earth itself has not cleared all objects from its orbital path. Near-Earth asteroids cross Earth's orbit continuously. Mars has not cleared the asteroid belt. Jupiter hasn't cleared its orbital path either. The Trojan asteroids orbit in the same path as Jupiter. The difference is degree, not kind. Alan Stern, the principal investigator of the New Horizons mission, has argued since 2006 that under a strict application of the IAU's own definition, Earth, Mars, Jupiter, Neptune, essentially all the planets, fail the clear the neighborhood criterion when you examine them carefully enough. The definition is not scientifically rigorous. It is vague in the ways that definitions cobbled together by committee tend to be vague. But the demotion stuck, not because the scientific case for it was airtight, but because the IAU process produced a formal resolution, and most media and educational institutions adopted it. Pluto became a dwarf planet. Textbooks were updated. School children were told what they had been taught was wrong. And a generation of people who grew up with 9 planets found out one morning that there were 8. The irony that New Horizons, the spacecraft that reached Pluto in 2015 and revealed it as a complex, geologically active, chemically rich world, was launched in January 2006. 7 months before the IAU vote, is not lost on anyone who has followed the story. The mission that would prove Pluto's extraordinary nature was in flight when the organization that governs astronomical nomenclature decided it was a minor body not worth full planetary status. Alan Stern launched the mission to study a planet. It arrived at a dwarf planet. The discovery it made would have been one of the greatest planetary discoveries of the century. Instead, officially, it was the greatest dwarf planetary discovery. The classification question is not purely semantic. It affects funding, mission prioritization, public interest, and, perhaps most importantly, the framework within which planetary scientists think about the objects they study. Whether Pluto is called a planet or a dwarf planet shapes which questions get asked about it and which objects get compared to it. And the New Horizons data, which revealed Pluto as far more complex and active than any body in the dwarf planet category had been imagined to be, has reinvigorated the argument about whether the current classification system serves science well. Some planetary scientists have proposed alternative classification systems that return to a simpler, geophysically based definition. Under these proposals, a planet is any round body that orbits a star and is not itself a star. This definition would include Pluto, Eris, Ceres, and perhaps 100 or more bodies in the solar system. But proponents argue that this is scientifically appropriate. There are genuinely many planet-like objects in the solar system, and pretending otherwise distorts how we think about planetary science. The IAU has not revised its 2006 definition. Pluto remains officially a dwarf planet. The argument continues. Let's spend some time with the engineering of New Horizons itself. Because the spacecraft is extraordinary in ways that most discussions of the mission skip over, and understanding what it took to build it changes how you understand what it achieved. The fundamental challenge of a Pluto mission is distance. 5.9 billion kilometers at Pluto's mean distance from the Sun. At the inner solar system, rocket speeds achievable with conventional propulsion, reaching that distance in any reasonable mission lifetime, required a gravitational assist, a flyby of a massive planet that would redirect and accelerate the spacecraft without requiring additional fuel. The chosen assist was Jupiter. New Horizons was designed to be fast, faster than anything previously launched, because every additional year in transit means additional cost, additional risk of component failure, additional time for the science team and their funders to lose patience with the project. The mission had already been cancelled once by NASA and restored after a public outcry and vigorous scientific advocacy. It couldn't afford to be a long, slow journey. When New Horizons launched in January 2006, it left Earth at 58,536 kilometers per hour, the fastest launch speed ever achieved for a spacecraft at that time. It crossed the Moon's orbit in just 9 hours. For comparison, Apollo missions took 3 days to reach the Moon. New Horizons covered that distance in less than 1 working day. The Jupiter flyby in February 2007 accelerated the spacecraft to approximately 83,000 kilometers per hour relative to the Sun. At that speed, New Horizons was gaining distance from the Sun faster than any other spacecraft had ever traveled. It broke the speed record previously held by Voyager 1. And yet, it took 9 more years to reach Pluto. The spacecraft itself weighs approximately 478 kilograms at launch, about the weight of a concert grand piano. It measures 2.2 meters across and has the general shape of a grand piano with a large dish antenna attached. The antenna, 2.1 meters in diameter, is the most critical component after the science instruments, because without reliable communication with Earth, the spacecraft's observations are worthless. The power source is a radioisotope thermoelectric generator, an RTG. No solar panels, at Pluto's distance from the Sun. Sunlight is so weak, about 1,000th of Earth's intensity, that solar panels of any practical size would generate insufficient power. Instead, the RTG converts the heat from the radioactive decay of plutonium-238 into electricity. At launch, the RTG produced about 240 watts, enough to power a few light bulbs, enough to operate a spacecraft 5 billion miles from the Sun. The science payload consists of 7 instruments: LORRI, Long-Range Reconnaissance Imager, a high-resolution telescopic camera that produced the detailed images of Pluto's surface. It achieved pixel scales of approximately 75 to 250 meters at closest approach, good enough to see features the size of large buildings. RALPH, actually a combined camera and spectrometer system with a colloquial name. Its MVIC, multispectral visible imaging camera, component produced the color images. Its LISA, linear echelon imaging spectral array, component produced the infrared spectral maps that revealed the composition of surface materials. ALICE, an ultraviolet spectrometer that analyzed the composition and structure of Pluto's atmosphere by observing the way sunlight was absorbed as it passed through the atmosphere. REX, radio science experiment, used the spacecraft's radio communication system to measure temperature and pressure profiles in Pluto's atmosphere by precisely measuring how the radio signal from Earth was bent and absorbed as the spacecraft passed behind Pluto. SWAP, solar wind around Pluto, measured the interaction between Pluto's atmosphere and the solar wind, the stream of charged particles continuously flowing outward from the Sun. PEPSISI, Pluto Energetic Particle Spectrometer Science Investigation, measured energetic ions escaping from Pluto's atmosphere. SDC, Student Dust Counter. Built by students at the University of Colorado, this instrument counted dust particles along the trajectory and provided the most detailed map of dust density in the outer solar system ever assembled. Each instrument was painstakingly calibrated, tested, and sequenced into the observation timeline for the flyby. The sequence of observations during the closest approach window, roughly 14 hours during which Pluto was close enough to image at high resolution, was planned down to the second. There was no margin for error. Every command had to be right before launch, because during the flyby itself, the spacecraft would be too busy observing to take instructions from Earth. And any instructions sent from Earth would take 4.5 hours to arrive anyway. The planning team spent years developing and refining this sequence. They ran simulations. They identified failure modes. They developed contingency plans for every scenario they could anticipate. And when the moment came, when New Horizons was actually flying past Pluto at 49,600 kilometers per hour, at closest approach, passing within 12,500 kilometers of the surface, it executed every command perfectly. The margin for error in the navigation was remarkable. To point LORE at specific surface features of Pluto during the brief close approach window, the spacecraft's position along its trajectory had to be accurate to within a few kilometers after 9 years of travel. The navigators achieved this through a combination of stellar reference measurements taken by the spacecraft itself, course corrections using the thrusters, small burns executed early in the mission when any error would have the longest time to compound, and extraordinarily precise orbital mechanics calculations that accounted for every gravitational influence along the route. What Alan Stern described as the equivalent of firing a sniper rifle and hitting a moving target the size of a dinner plate from 10 miles away, 9 years after pulling the trigger, was, in fact, somewhat underselling it. It was a dinner plate moving at 14 kilometers per second. New Horizons revealed Pluto. But Pluto is not alone where it lives. The Kuiper Belt, the vast, disc-shaped region of the solar system extending from roughly Neptune's orbit at 30 ATUs to about 50 ATUs from the Sun, contains somewhere between 100,000 and possibly millions of objects larger than 100 kilometers in diameter, plus an unknown number of smaller bodies that shade off into the size range of interplanetary dust. Understanding Pluto properly requires understanding the Kuiper Belt, because Pluto is not an anomaly within it. Pluto is the Kuiper Belt's largest and most easily studied member, and what New Horizons found at Pluto tells us things about the rest of the belt that we cannot yet verify directly, because we haven't sent spacecraft to those other bodies. The Kuiper Belt is not evenly distributed. It has structure imposed by the gravitational influence of Neptune, which dominates the outer solar system the way Jupiter dominates the inner. Neptune's gravity has cleared some orbital regions and concentrated objects in others, creating families of objects with specific orbital relationships to Neptune. Pluto belongs to a family called Plutinos, objects whose orbital period stands in a 2 to 3 resonance with Neptune. For every 3 orbits Neptune completes, a Plutino completes exactly 2. This resonance is gravitationally stable. Any object that happens to enter it tends to stay in it, because the specific pattern of gravitational kicks from Neptune averages out over time to produce no net change in the orbit. Pluto has been in this resonance for the entire history of the solar system. There are hundreds of known Plutinos. Pluto is by far the largest, but others are substantial. Orcus, with a diameter of roughly 910 kilometers, is the second largest Plutino. It has a large moon, Vanth, discovered in 2005. Its orbit is almost a mirror image of Pluto's. Their orbital orientations are opposite, in a way that means they never come close to each other, despite following similar resonant patterns. Beyond the Plutinos, the classical Kuiper Belt, sometimes called the cold classical belt, because its objects have relatively circular, low-inclination orbits, contains a distinct population of objects that have likely never been perturbed significantly since they formed. These are among the most pristine samples of the original solar nebula material available anywhere in the solar system. Their surface compositions, their internal structures, their orbital properties all reflect the conditions in the outer solar system 4.5 billion years ago. preserved in the cold of the Kuiper Belt through the entire subsequent history of the solar system. Arrokoth, the object New Horizons visited after Pluto in January 2019, belongs to this cold classical population. It became the most distant object ever visited by a spacecraft. At the time of the flyby, roughly 6.6 billion kilometers from the Sun. What New Horizons found there was as scientifically significant in its own way as the Pluto flyby, though it received far less public attention. Arrokoth is a contact binary. Two distinct lobes pressed gently together, forming a shape that early images compared to a snowman. The larger lobe, approximately 21 kilometers across, was named Wenu. The smaller, approximately 15 kilometers across, was named Wio. The contact between the two lobes is gentle, not a violent collision but a slow coming together of two objects that were already orbiting close to each other. The surface of Arrokoth shows no evidence of the fracturing or compression that a high-speed impact would produce. The join between Wenu and Wio is smooth, their surfaces flowing continuously into each other, as if two spheres had been slowly pressed together by a hand rather than thrown at each other. This gentle joining has a specific implication for the theory of how small bodies in the solar system form. The prevailing model at the time of New Horizons' launch was planetesimal formation by pairwise accretion. Small particles collide and stick together, gradually growing larger through successive collisions, each one adding mass to the growing body. This model works mathematically, but has difficulty explaining certain observed properties of small bodies in the outer solar system, particularly the gentle binary configurations observed in the cold, classical Kuiper Belt. An alternative model, called pebble cloud collapse or streaming instability, proposes that particles in the early solar nebula could concentrate into dense clumps under certain conditions, and these clumps could directly collapse under their own gravity into binary pairs without requiring individual particle-by-particle accretion. In this model, Wenu and Wio would have formed together in the same local collapse event, orbited each other from their earliest formation, and then slowly spiraled together over billions of years as tidal interactions between them dissipated orbital energy. Arrokoth's morphology, the gentle contact, the smooth join, the similar surface composition of both lobes suggesting they formed in the same environment, is consistent with the cloud collapse model and inconsistent with the violent accretion model. The New Horizons team's analysis of the flyby data, published in 2020 in Science, concluded that pebble cloud collapse is the most likely formation mechanism for Arrokoth, and, by extension, for many other small bodies in the cold classical Kuiper Belt. This is a revision of planetary formation theory from first principles observation, not a refinement of existing models, but a test that distinguished between competing models and identified which one fits the observed reality. The significance extends beyond Arrokoth. If cold classical Kuiper Belt objects form by cloud collapse rather than pairwise accretion, the initial conditions of planetary formation in the outer solar system were different than previously assumed. The consequences for understanding how the giant planets formed and how the solar system reached its current configuration are substantial. Arrokoth's surface is also notably red, redder than many Kuiper Belt objects, redder than Pluto's brightest regions, with a color consistent with the organic rich material called tholins that we've already encountered on Pluto and Charon. The tholins on Arrokoth are ancient, billions of years old, preserved in the cold of the Kuiper Belt's outer reaches, essentially unchanged since the solar system's earliest epoch. They represent the original organic chemistry of the outer solar system, the raw material from which more complex chemistry could develop given time and energy. Let's be specific about the evidence for Pluto's subsurface ocean, because the question, does Pluto have a liquid water ocean, is one of the most important questions in planetary science. And the answer is more nuanced than either yes or no captures. The evidence is indirect. No instrument on New Horizons could directly detect liquid water beneath Pluto's surface. The spacecraft had no ground-penetrating radar, no seismometer, no gravimetric survey instrument that could reveal internal structure with the kind of precision needed for direct ocean detection. What it had were cameras, spectrometers, and atmospheric sensors, instruments designed for surface and atmospheric characterization. The ocean hypothesis rests on 4 independent lines of evidence, each suggestive but not individually conclusive. The first is the expansion cracks. Pluto's surface shows extensive fracturing, long linear features that suggest the crust has been pulled apart. On Earth, surface extension like this occurs when the lithosphere stretches, either from tectonic spreading or from an expanding interior. On Pluto, the most natural explanation for surface extension is that the interior expanded. And the most natural way for a planetary interior to expand is for liquid water to freeze. Water expands when it freezes, a familiar property exploited by anyone who's ever left a water bottle in the freezer too long. If Pluto had a subsurface ocean that has been gradually freezing over geological time, the expanding ice would push the crust apart, producing exactly the extensional fractures observed. The geometry of the fractures is consistent with this interpretation. They are not randomly distributed, but concentrated in regions and orientations that match what would be expected from an expanding interior. The second line of evidence is Sputnik Planitia's position. The nitrogen ice-filled basin is located very close to the sub-Charon point, the point on Pluto's surface that faces Charon. This is not obviously a coincidence. Charon's gravity pulls on Pluto, and if Pluto were fluid enough to respond, any large mass concentration on Pluto's surface would tend to migrate toward the equatorial plane of the Pluto-Charon orbit, due to tidal torque from Charon. If Sputnik Planitia represents a mass concentration, a deep basin filled with dense nitrogen ice, tidal forces from Charon could have gradually reoriented Pluto so that the basin migrated toward the sub-Charon point over geological time. This reorientation, called true polar wander, requires that Pluto's interior was fluid enough over geological time to allow the surface to drift relative to the rotation axis. A rigid, completely frozen Pluto could not do this, but a Pluto with a liquid internal layer, the subsurface ocean, could. The ocean would have allowed enough interior mobility for the tidal torque to gradually reorient the crust. The third line of evidence is the topography of the basin itself. Sputnik Planitia is a depression, several kilometers deep relative to the surrounding terrain. If Pluto were completely frozen and homogeneous, a large depression of this kind would gradually relax over geological time. The ice beneath would slowly flow outward, filling the depression. The fact that Sputnik Planitia persists as a deep depression suggests that either it is continuously maintained by active processes, or that the material beneath it is rigid enough not to flow, which is inconsistent with a completely frozen interior at depth. A liquid ocean beneath a rigid ice shell would support the topography above it hydrostatically, allowing the depression to persist. The fourth line of evidence is the 2019 detection of fresh ammonia in surface fractures. Fresh ammonia means recently emplaced ammonia, material that arrived at the surface geologically recently, since ancient ammonia would have been destroyed by cosmic radiation over millions of years. The most natural source for fresh ammonia-bearing material on Pluto's surface is eruption from depth. Cryovolcanic activity bringing ammonia water mixture from the subsurface to the surface through fractures in the ice shell. If this interpretation is correct, the subsurface ocean is not just potentially present. It is actively communicating with the surface. Material is moving between the ocean and the surface right now, or at least within the last few million years, which in geological terms is essentially now. The combined weight of these 4 lines of evidence has persuaded most planetary scientists working on Pluto that a subsurface ocean is the most parsimonious explanation. The explanation that accounts for all the observations with the fewest additional assumptions. This does not mean it is certain. An ocean has not been directly confirmed, but it is the leading hypothesis, and the hypothesis that the scientific community has largely coalesced around. What does that ocean look like physically? Based on thermal models that incorporate Pluto's composition and internal heat production, the ocean would be located at depths of roughly 100 to 200 kilometers below the surface. Its thickness is uncertain. Estimates range from a few tens of kilometers to several hundred. The temperature of the ocean would be above the freezing point of the ammonia water mixture it contains, somewhere in the range of -70 to -40 degrees Celsius, depending on ammonia concentration. The pressure at that depth would be tens of megapascals, much higher than Earth's ocean pressure at comparable depths, because Pluto's ice shell above the ocean is denser than liquid water. The ocean sits in the dark, completely enclosed, never seeing the sun or the stars, fed heat from below by the radioactive decay in Pluto's rocky core and by whatever residual formation heat remains, chemically rich with dissolved ammonia and probably other compounds from the rock it contacts at the base of the ocean. Whether anything lives in it is a question the current state of knowledge cannot answer. We cannot definitively rule it out. Every treatment of Pluto's subsurface ocean eventually gets to the question of life. The competitor video handled this by briefly mentioning extremophiles, acknowledging that ammonia is toxic, then immediately reversing to say maybe bacteria could evolve to use it. This is not wrong, but it's not the full picture. Let's do the honest version. The conditions in Pluto's potential subsurface ocean are extreme by Earth standards. But extreme is not the same as incompatible with life. Earth harbors life in environments that would have been considered impossible for biology by scientists a century ago. Hydrothermal vents on the ocean floor where temperatures exceed 400 degrees Celsius. Acidic hot springs with pH values near 0. Antarctic ice sheets where liquid water exists only in thin films between ice crystals. The interior of nuclear reactors where some microorganisms survive radiation doses that would be lethal to virtually any complex organism. These extremophiles, organisms adapted to extreme conditions, extend the known boundaries of the biosphere continuously as scientists look in new places. So what would Pluto's ocean need to support life? The same basic requirements that apply everywhere life has been found. A liquid solvent, an energy source, and available nutrients. The liquid solvent is potentially present, the ammonia water mixture. But this is where the honest version diverges from the optimistic version. Ammonia at the concentrations proposed for Pluto's ocean, 20 to 30% by weight, is genuinely challenging for Earth-based biochemistry. It is not simply toxic in the way that cleaning products are toxic. At high concentrations, ammonia actively disrupts the hydrogen bonding that holds proteins and nucleic acids together. It disrupts lipid bilayer membranes, the structures that form cell walls in all known life. Earth life uses water as its biochemical solvent, precisely because water's hydrogen bonding properties are compatible with the molecular structures of life. Ammonia, while also capable of hydrogen bonding, has different properties that would require completely different molecular architectures for any biochemistry built around it. This is not impossible. Theoretical biochemists have explored the possibility of ammonia-based life, and the basic chemistry is not prohibited. But It would be genuinely alien biochemistry, not just Earth life that tolerates ammonia, but organisms with fundamentally different molecular foundations. Nothing we know about the origin of life on Earth tells us how likely this is to arise spontaneously. The energy source question is also complex. Earth's deep-sea extremophiles near hydrothermal vents get their energy from chemosynthesis, chemical reactions between hot, mineral-rich vent fluid and the cooler surrounding ocean water. The chemical gradients at these vents provide a continuous energy supply. Pluto's ocean is not driven by hydrothermal vents in the same sense. The heat source is radiogenic, uniformly distributed throughout the rocky core rather than concentrated in specific vent locations. This means the energy gradient that would drive chemosynthetic life is less steep and less localized than in Earth's deep-sea vent environments. There are potential chemical energy sources in Pluto's ocean. Oxidants produced by cosmic radiation hitting the surface, hydrogen peroxide, molecular oxygen, various reactive oxygen species, could be transported to the ocean through the fractures in the ice shell that the fresh ammonia evidence suggests are active. If oxidants from the surface reach the ocean, they could react with reduced compounds in the ocean water, releasing chemical energy that life could in principle exploit. This mechanism is proposed for the potential ocean of Europa around Jupiter and is considered a plausible energy source for life there. The nutrient question is the most speculative. Complex life requires more than just liquid water and energy. It requires the specific atoms, carbon, nitrogen, phosphorus, sulfur, and various trace metals, in forms that can be incorporated into biochemistry. Pluto's rocky core contains these elements. Whether the interaction between the ocean water and the rock at the base of the ocean is sufficient to bring them into solution in usable forms depends on details of the ocean chemistry and the rock water interface that are currently unknown. The honest assessment: Pluto's potential subsurface ocean is not obviously hospitable to life, and it is not obviously incompatible with life. The honest statement is simply that we do not know. The environment is extreme by Earth standards, requires chemistry we have not observed life using before, and lacks some of the energy gradient characteristics of the most life-friendly extreme environments we know about. But Earth life occupies a narrow slice of the possible biochemical parameter space, and life adapted to very different conditions might be possible. The only way to get a more definitive answer would be a mission that could directly sample and analyze the ocean, which brings us to what comes next. New Horizons answered many questions about Pluto. It also generated new ones. And the planetary science community has been working, since the flyby data began arriving, on the question of what kind of follow-up mission would be needed to address the most important unanswered questions. The highest priority unanswered question is the subsurface ocean. Confirming or disconfirming the ocean's existence requires an instrument that New Horizons did not have: a ground-penetrating radar. This technology, used on Mars by the SHARAD instrument on NASA's Mars Reconnaissance Orbiter and the MARSIS instrument on the European Space Agency's Mars Express, can detect subsurface layers by bouncing radio waves through the ground and detecting the reflected signals from boundaries between different materials. An orbiting spacecraft with ground-penetrating radar at Pluto could map the depth of the ice shell, detect the boundary between ice and any liquid layer beneath, and characterize the ocean's thickness and structure. But getting an orbiter to Pluto is far harder than getting a flyby spacecraft there. A flyby spacecraft doesn't need to slow down. It just passes through. An orbiter needs to decelerate from the enormous velocity required to reach Pluto in a reasonable time, using either propellant carried from Earth or aerocapture, using atmospheric drag to slow down. Pluto's atmosphere is far too thin for effective aerocapture. Propellant for propulsive orbital insertion would be the dominant mass of the spacecraft, driving up cost and potentially requiring a larger, more expensive launch vehicle. Various mission concepts have been studied. A direct propulsive orbiter is the simplest concept but requires enormous propellant mass. A flyby with probe deployment. A spacecraft that conducts a flyby like New Horizons but releases a small atmospheric probe and/or surface penetrators during the flyby. Could gather atmospheric and surface chemistry data without requiring full orbital insertion. A more exotic concept involves using nuclear electric propulsion, a nuclear reactor powering electric thrusters that provide continuous low-thrust acceleration, eventually reaching Pluto in a decade or more, but with enough propellant efficiency to actually orbit when they arrive. This technology has been demonstrated in limited form. NASA's Dawn mission used ion propulsion to orbit first Vesta and then Ceres in the asteroid belt. But scaling it for a Pluto orbiter mission is a substantial engineering challenge. In the 2023 to 2032 Planetary Science and Astrobiology Decadal Survey, the comprehensive priority-setting document produced every decade by the planetary science community. A Pluto system mission was identified as a priority within the Outer Solar System exploration portfolio. This doesn't guarantee funding, but it establishes scientific consensus that a follow-up mission is warranted. The question is when and in what form. Any mission launched in the next decade would reach Pluto no earlier than the late 2030s or early 2040s, given travel times. The science questions that New Horizons raised will remain partially unanswered for at least another decade and a half, possibly longer. The planetary science community is not passive about this. Active research programs analyzing the New Horizons data continue to extract new insights. Laboratory experiments simulating Pluto's surface chemistry and atmospheric photochemistry provide ground truth for interpreting spectroscopic observations. Telescopic observations from Earth and space track Pluto's seasonal changes. The atmosphere is monitored for changes in pressure and composition as Pluto moves along its eccentric orbit, and the balance between sublimation and condensation shifts. Pluto is being studied, just not as rapidly as the richness of its geology warrants. The discoveries at Pluto do not end at Pluto. They have implications for the entire Kuiper Belt and for how we think about the distribution of potentially habitable environments in our solar system. Before New Horizons, the conventional picture of habitable environments in the solar system was relatively simple. Habitability required proximity to the Sun, the so-called habitable zone. The range of distances at which a planet could maintain liquid water on its surface given a particular stellar luminosity. Earth sits in the Sun's habitable zone. Mars is at its outer edge. Venus is too close and too hot. Beyond the habitable zone, conventional thinking said, surfaces are frozen and interiors are geologically inert. This picture was already challenged before Pluto by the discoveries at the icy moons of Jupiter and Saturn, Europa, Enceladus, Titan, Ganymede, all of them far outside the Sun's habitable zone, were found to have liquid water oceans or other complex chemical environments maintained by tidal heating from the gravitational interactions with their parent planets. The habitable zone, it became clear, was not the only place in the solar system where liquid water could persist. But Europa and Enceladus and the other active moons depend on tidal heating. They need the proximity of a massive planet to supply the gravitational energy that keeps their interiors warm. Pluto has no such massive parent. It orbits the Sun directly, far from Jupiter or Saturn. Its interior heat comes entirely from radiogenic decay and residual formation heat. If Pluto has a liquid subsurface ocean maintained by internal radiogenic heat alone, with no tidal contribution, then the implication is profound. Any sufficiently large, rock-rich, icy body in the solar system might have a subsurface ocean. Not just Pluto, but the dozens of other substantial Kuiper Belt objects. Not just in the solar system, but in the billions of icy bodies orbiting in similar positions around other stars throughout the galaxy. This completely transforms the estimate of how many potentially habitable environments exist in the universe. If habitable conditions require only a sufficient size, sufficient rock content for radiogenic heat, and the presence of water ice with an antifreeze compound, conditions that should be common in planetary systems throughout the galaxy, then the number of potentially habitable places in the universe is not in the billions, but in the trillions or quadrillions. Most of these bodies would be small, dark, far from their stars, and orbiting in the cold regions of planetary systems. Nothing about them would suggest habitability from the outside. They would look exactly like Pluto looked to Earth-based telescopes before 2015, a small, dim, featureless dot at the edge of the observable solar system. Cold, dead, boring. And some of them might have liquid water underneath their ice. Warm, chemical, dark, pressurized liquid water, sustained by the heat of radioactive rocks, enriched by the chemistry of rock-water interaction, possibly supplied with oxidants from their icy surfaces through fractures and cryovolcanic activity. If life requires liquid water and chemical energy, and if both are present in subsurface oceans maintained by radiogenic heat throughout the galaxy, then the number of potentially inhabited worlds in the universe is not thousands or millions. It might be astronomical. New Horizons did not find life at Pluto, but what it found may have expanded the inventory of places where life could be by a factor of many billions. One of the most striking things about Pluto's atmosphere is that it is temporary, not in the cosmological sense of everything being temporary, but in the immediate measurable sense of ongoing collapse. Pluto's orbit is highly elliptical. Its distance from the Sun varies from about 4.4 billion kilometers at perihelion, closest approach, to about 7.4 billion kilometers at aphelion, farthest distance. The orbital period is 248 years. Pluto reached perihelion in 1989 and is currently moving away from the Sun, getting progressively colder. As Pluto recedes from the Sun and the surface temperature drops, the volatile ices that sustained the atmosphere during the warmer decades begin to condense. Nitrogen, the primary atmospheric gas, is the key. When the surface temperature drops below the nitrogen condensation point for the current atmospheric pressure, nitrogen begins freezing out. Ice forms on the surface. The atmosphere loses mass. As it loses mass, the pressure drops. As pressure drops, the condensation temperature also drops slightly. The process accelerates. The result is a collapse. Pluto's atmosphere doesn't gradually thin over decades. It will, at some point in the coming years or decades, collapse relatively rapidly as the nitrogen condensation runaway takes hold. The entire atmosphere, currently containing roughly 10 to 20 milligrams of nitrogen per square centimeter of Pluto's surface, will freeze onto the surface as a thin global frost. The blue haze, the 12 atmospheric layers, the photochemical processing of methane into tholins, all of it will stop. Pluto's sky will literally fall. This is not a catastrophic event in any sense that matters on human timescales. It happens every 248 years as Pluto completes an orbit. It has happened billions of times in Pluto's history. The atmosphere rebuilds when Pluto returns to perihelion, and the surface warms enough to sublime the nitrogen frost back into gas. But we are watching it happen right now. Ground-based observations of Pluto's atmospheric pressure measured by watching how the atmosphere bends starlight when Pluto occults a background star, have tracked the atmospheric pressure continuously since the 1980s. After New Horizons confirmed the current state of the atmosphere in detail, follow-up occultation observations in 2019, 2020, and beyond have detected the beginning of the decline. The atmospheric pressure has not yet dramatically decreased. The collapse may be decades away, but the trend is measurable. At some point in the early to mid-21st century, Pluto's atmosphere will collapse. The blue haze will vanish. The winds that sculpted the dune fields of Sputnik Planetia's margins will stop. The nitrogen cycle will pause, waiting for the distant sun to warm the surface again a century from now. The timing of this collapse could interact with any future mission to Pluto in important ways. A mission arriving during the atmospheric collapse phase would observe different conditions than New Horizons observed in 2015. The atmosphere would be thinner, its interactions with the surface chemistry different, the haze layers absent or greatly reduced. A mission arriving after a full collapse or during the rebuild phase would observe yet another state. Pluto, at different points in its 248-year orbital cycle, is, in a meaningful sense, a different world. Not structurally different, but atmospherically and chemically different. Scientists who want to understand the full range of Pluto's behavior need observations at multiple orbital phases. New Horizons caught one moment, near the atmospheric maximum following the 1989 perihelion. Future missions will catch other moments. Together, they would build a picture of a genuinely dynamic world, cycling through different states over its 248-year year. Among the discoveries that best illustrate the principle that Pluto violates all intuitive expectations is the discovery of dunes. In images of the margin between Sputnik Planitia and the highlands terrain to its south, New Horizons detected regularly spaced ridges, undulations in the surface with a spacing of roughly 400 to 1,000 meters, oriented in a consistent direction relative to the prevailing topography. The geometry is unmistakable to anyone who has seen desert dunes on Earth or sand dunes on Mars. These are dunes. Dunes require wind. Wind requires atmosphere. Pluto has an atmosphere, thin but real. The question is whether the atmosphere is thick enough to move particles across the surface. On Earth, dunes form when wind velocity exceeds the threshold needed to lift and transport sand grains. The threshold depends on the size and density of the grains and the density of the transporting fluid. On Mars, which has an atmosphere about 1% as dense as Earth's, dunes form but require higher wind speeds than on Earth. On Pluto, where the atmosphere is 100,000 times less dense than Earth's, naively, you would expect the threshold wind speed for particle transport to be enormous, far beyond what Pluto's feeble atmospheric circulation could achieve. The resolution to this apparent contradiction comes from the properties of the particles being transported. They are not sand. They are methane ice crystals, tiny, light particles with densities far lower than quartz sand. The lower density of the particles dramatically lowers the threshold wind speed needed to move them. Combined with the specific conditions on Sputnik Planitia, where nitrogen sublimating from the plane's surface creates upward-flowing gas currents that can loft methane particles, the threshold for dune formation turns out to be within the range of Pluto's actual atmospheric winds. The dunes at Sputnik Planetia's margin are therefore wind-driven features. They are formed from methane ice crystals carried by nitrogen sublimation winds and deposited in characteristic dune patterns. They are, in their essential physics, the same phenomenon as Earth's sand dunes or Mars's dust dunes. The materials are completely different, the mechanism is the same. This discovery, confirmed in a 2018 paper in Science, demonstrated that aeolian, wind-driven, geology is not a special property of Earth and Mars, but can operate in environments far beyond what the conventional habitable zone suggests. Any world with both a surface volatile and an atmosphere, however thin, can potentially support wind-driven surface geology. This principle, established at Pluto, has implications for how we interpret surface features on other icy bodies throughout the solar system. Beyond the surface geology and the atmospheric chemistry, New Horizons measured something about Pluto that is completely invisible to any telescope: its interaction with the solar wind. The solar wind is the continuous outflow of charged particles, mostly protons and electrons, from the Sun. It flows outward through the solar system at roughly 400 to 800 kilometers per second, filling the space between planets with a tenuous but dynamically significant plasma. Every body in the solar system with an atmosphere or a magnetic field interacts with the solar wind in specific ways. Pluto has no significant global magnetic field. The measurements from New Horizons confirmed that any internal dynamo, if it ever existed, has long since shut down. Without a magnetic field, Pluto cannot deflect the solar wind. Instead, the solar wind flows directly into Pluto's upper atmosphere, ionizing the uppermost atmospheric molecules through a process called charge exchange. The ionized atmosphere is then carried away by the solar wind. Essentially, Pluto is continuously losing atmospheric material to the solar wind, which picks up the ionized particles and sweeps them downstream into a long cometary tail extending hundreds of thousands of kilometers in the anti-sunward direction. SWAP and PEPSI, two of the New Horizons instruments specifically designed to measure this interaction, detected Pluto's atmospheric tail extending at least several million kilometers downstream. The rate of atmospheric escape is not catastrophic. New Horizons measured escape rates roughly 10,000 times lower than some pre-flyby predictions. But it is real and ongoing. This atmospheric escape has an important implication for Pluto's long-term history. Over 4.5 billion years of solar wind interaction, Pluto has lost a measurable amount of its original volatile inventory to space. The current atmosphere represents a steady state between sublimation adding gas from the surface and solar wind stripping removing gas from the top. If the sublimation rate were to drop permanently, as it will when the Sun eventually becomes a red giant and then a white dwarf, the solar wind stripping would eventually remove the atmosphere entirely. But on the time scale of the Sun's current main sequence life, the balance is maintained. Sublimation replenishes what the solar wind takes away. Pluto keeps its atmosphere. The lower-than-expected escape rate had an additional significance. It meant that the original models of Pluto's atmospheric evolution were wrong. If the escape rate is 10,000 times lower than predicted, Pluto has lost 10,000 times less of its volatile inventory to space than the models assumed, which means Pluto's current volatile inventory may be much closer to its original inventory than predicted. The nitrogen, methane, and carbon monoxide ices currently present on Pluto's surface may represent a larger fraction of the original volatile budget than anyone expected. The implications cascade. If Pluto still retains most of its original volatile inventory, its interior chemistry is less depleted than assumed. The subsurface ocean, if present, may be richer in dissolved volatile compounds than models based on assumed escape rates would predict. The photochemical products of Pluto's atmosphere, the tholins, have been accumulating on the surface at a rate tied to the atmospheric methane abundance, which is tied to the volatile inventory. All of these factors interconnect in ways that the lower escape rate changes significantly. It is worth being explicit about something that distinguishes New Horizons from most mission discussions. The analysis is ongoing, and it keeps producing new findings. The raw data from the flyby was all downloaded and archived by late 2016. Since then, scientists have been analyzing it continuously. Not the same scientists looking at the same images. New researchers entering the field, applying new analysis techniques, looking at the data with questions that weren't being asked in 2015. Some of the most significant post-flyby findings came years after the data arrived. In 2017, a paper in Nature described the results of careful analysis of LORRI images, showing the evolution of features near the edges of Sputnik Planitia over the brief period that New Horizons observed them. The spacecraft was close enough to Pluto long enough to detect actual changes in some features between early approach images and close approach images. The changes were subtle but measurable, evidence of active sublimation of nitrogen ice occurring in real time during the observation period. In 2019, the detection of fresh ammonia near fractures was announced. Data that had been in the archive since 2015, but required careful spectral analysis against background contamination to extract reliably. In 2020, a detailed analysis of the bladed terrain was published that refined the altitude dependence model and showed that the blades are growing, currently being sculpted by ongoing sublimation, rather than being static features left from a past atmospheric state. In 2021, the comprehensive cryovolcanism study of Wright Mons and Picard Mons argued more definitively than previous analyses that these are genuine volcanic edifices and that the material around them represents recent cryovolcanic deposits. In 2022, a paper analyzing the detailed color mapping of Pluto's surface revealed spatial patterns in the Tholin distribution that are inconsistent with simple atmospheric deposition and suggest active redistribution of organic material by nitrogen ice transport, the nitrogen cycle carrying organic compounds from the atmosphere across the surface. Each of these findings was in the data all along. They were extracted as analytical techniques improved, as more scientists looked at the data, as new theoretical frameworks suggested new questions to ask of the observations. The implication: the New Horizons dataset is not a closed book. It is an ongoing resource. Scientists will be publishing new findings from the 2015 Pluto flyby for decades. The spacecraft passed Pluto once, for a few hours, at the closest approach, but the data it collected during those hours and during the weeks of approach and departure, when Pluto was observable at moderate resolution, is rich enough to support years of discovery beyond the initial flyby. This is partly a function of how science works in the data-rich era of planetary exploration. Spacecraft are expensive and rare, so their observations are analyzed with more care over longer periods than any other scientific dataset. But it is also a function of Pluto's genuine complexity. A simpler world, one that looked more like pre-flyby expectations, would have been analyzed more quickly. Pluto keeps revealing new things because there are new things to reveal. Let's end where the data leads us, which is a different place from where we started. Before July 14, 2015, Pluto was a data point, a distant, dim, small object whose properties were known in outline but not in detail. It was at the edge of the solar system, far from the sun, cold, small, likely dead. Its main scientific interest was what it might tell us about the outer solar system's general properties: composition, orbital dynamics, the population of the Kuiper Belt. After the New Horizons data, Pluto is a world, a specific, individual, internally complex world, with its own geological history, its own atmospheric cycle, its own chemistry, its own possible interior ocean, its own ongoing exchange of material with its companion Charon and the broader Kuiper Belt. It is not a representative sample of the outer solar system. It is a place. This distinction between a data point and a place is not just rhetorical. It changes what questions we ask and what answers are available. A data point asks, what are the statistical properties of outer solar system bodies? What fraction have atmospheres? What fraction have volatile ices? What fraction are geologically active? A place asks, how did this specific geology form? What is the history of this specific organic chemistry? What drove the specific nitrogen cycle features visible in these specific images? What does the presence of these specific fractures tell us about the specific interior of this specific world? Place-based science is richer than statistical science, even though statistical science is important for understanding populations. The shift from Pluto as data point to Pluto as place is the shift that New Horizons achieved, and the place New Horizons revealed is genuinely extraordinary. Not in the sense that it is unique in the universe. The processes that drive Pluto's geology, atmosphere, and chemistry are probably common throughout the galaxy, but extraordinary in the sense that it represents a class of world we didn't know existed. Geologically active small bodies, maintained by radiogenic heat and volatile cycle feedbacks, in the cold outer reaches of planetary systems, potentially harboring liquid water beneath their surfaces. This class of world, if it is common throughout the galaxy, and the physics suggests it should be, may be among the most abundant, potentially habitable environments in the universe. Not the most dramatic. Not worlds with surface oceans and sunlit photosynthesis and complex ecosystems visible from orbit, but small, dark, cold on the outside, possibly warm and chemically active on the inside. Quiet, patient, waiting for someone to look closely enough. New Horizons look closely enough. What it found has changed how we see the solar system, and by extension, how we think about the universe. The specific wrongness of the pre-Flyby consensus is not an embarrassment. It is the most useful thing science can produce, a clear demonstration of where our models were failing, specific enough that we can identify what was missing and build better models. Every wrong prediction about Pluto, that it was geologically dead, heavily cratered, atmospherically simple, chemically inert, contained within it the seeds of understanding. Each one, revised against the actual data, has generated new insight. We sent a spacecraft 4.67 billion miles to find out we were wrong about a world. And in being wrong, we learned more about the universe than we could have by being right. That is what space exploration is for. Wherever you are tonight, whatever city, whatever country, whatever corner of this specific planet, tell us in the comments. We read them. The geography of who's out there listening to this matters to us. And if tonight gave you something to think about in the quiet before sleep, like the video and subscribe to Calm Theory for Sleep. The universe is not running out of things to show us. Pluto proved that. Sleep well.